All right, let's do a couple videos. I don't know why I always record these like right before student hours. I'm pretty sure we have time though. I won't go too fast. If I go too fast, you let me know and ask me if something doesn't make sense. We're going to start with number 146. Find the value or values of k that make the function continuous over the given interval. All right, so we're looking at 146. That's f of theta is a piecewise function, and it's equal to sine of theta between 0 and 2 pi. 0 to 2 pi inclusive on the left. Pi over 2, not 2 pi, right? Yeah, and it's cosine of theta plus k in the other half of the interval. All right, and this one is closed on both sides. So what value or values of k make this continuous? So for continuous on a closed interval, has to be continuous, one-sided continuity at the end. And in fact, we have continuity almost everywhere already, just because trig functions are continuous. All right, so trig functions are continuous. The only point we have to worry about is where they meet on this piecewise function. Each piece is continuous for all, I don't think I've introduced that notation yet, for all real numbers x or theta. So the only point we really have to worry about is it continuous where they meet? The only thing that matters is when theta equals pi over 2. So we'll look at the one-sided limit and make sure it equals the function value and make sure that equals the other one-sided limit. The limit as theta goes to pi over 2 from the left of this function. We'll have to calculate that, and we'll have to calculate the limit, from the left, as theta goes to pi over 2 from the right of this function. When are they equal to each other? If they're equal, then the limit exists. And we know that the limit will equal the function value if it exists, because this is a continuous function right here. So from the left, that's going to be the limit. Theta approaches pi over 2 from the left. If we're to the left of pi over 2, we're using this piece. Sine of theta. And sine is continuous, so this one-sided limit is just when you plug in pi over 2. That's the y value on the unit circle at 90 degrees, which is 1. And again, from the right, that's using this piece. That's going to be the limit. Theta approaches pi over 2 from the right of cosine of theta plus k. Oh, there's no room. And again, cosine's continuous. So this is going to be cosine of pi over 2 plus k. So when do these equal each other? So these are the same when they're equal, which is a little redundant, but when 1 equals the cosine of pi over 2 plus k. And now you get to solve a trigonometric equation. If you thought you were done solving trig equations, you thought wrong. So when is cosine of something, let's call this x, right, cosine of x equals 1, that's when the x coordinate on the unit circle is 0 degrees. Right, cosine equals 1, cosine's the x coordinate on the unit circle. So what angle is that? Well, it's 0, it's 2 pi, it's 4 pi, etc. And in fact, it goes in both directions. We can just write 0 plus 2 pi k, or just the 2 pi k would be fine. There are infinitely many solutions to this. But again, we don't care about x. What is x? X is pi over 2 plus k. So the limit exists and the function is then continuous when pi over 2 plus k Oh crap, I'm using different. Can't use k for this. We're already using k. 2 pi n, where n is some natural number or some integer. So it's true in pi over 2 plus k is equal to 2 pi n. What does k have to be? Subtract pi over 2. You could write it like this. A lot of times you'll actually see it written like this though. Again, this is where n is any integer. So there's infinitely many values of k that make this continuous. Yeah, there's no way I'm finishing this video in time. Well, this video is going to be split up. Because I really want to show you what this looks like. This is really cool. Get ready to be amazed. I'm excited to just show this to you. Even though I would like to get this finished in time, I'm way more prioritize this. Let's graph this piecewise function. It's sine of theta. I'm going to use x's here because Desmos likes it. It's sine of theta in this interval. And in the other interval, it's cosine of x plus k. Where k, and then again, this is on the interval pi over 2, less than or equal to x, less than or equal to pi. Now in Desmos, you can do something called add a slider. So when k equals 1, you can see what this function looks like. As we look at, I'm changing the value of k. Oh, it's continuous. At about approximately k equals negative 1.6. Was that one of our answers? I hope so. All right, pi over 2 is about 1.5. All right, yeah, it's kind of hard to see. You have to do some ones. Let's do hold on. Let's watch this. 2 pi n minus pi over 2. If n is equal to 0, that's 1.6. So yeah, this was one of our things. And then we can keep on making k smaller and smaller as this is the function as k gets smaller. As k gets smaller. Oh, looks like it's continuous again. Is that another value of n? Yeah, that's when n equals negative 1. And we keep on doing this, right? There's infinitely many values of k that make this continuous. And as we change k, the piecewise function changes. That's kind of cool, right? Come on, that's cool. I think it's cool. All right, so that's what we did. There's infinitely many. All right. I don't know how many people watch these videos, but this is cool. Do 156, and then we'll do the last two problems in the second half of the video. All right. Let f of x be that rational function. Sketch it and try to make this continuous. So let's sketch this with Desmos. X to the fourth minus 1, x squared minus 1. X to the fourth minus 1 divided by x squared minus 1. And this is true as long as x is not equal to negative 1 or positive 1. So there's actually holes. There's holes at negative 1 and positive 1. You could plot them if you wanted. 0.1 comma 2 and negative 1 comma 2. You wanted to hold left click on this dot, making an open circle in blue. Hold left click on this dot, making an open circle in blue. So this is what the function looks like. And it says, so we sketched it, that's part A. And I'll try to be clear on whether you need to copy it down or not. Here, you do not need to. Is it possible to find constants k? Is it possible to define this function at these points to make f continuous everywhere. Here's another way of phrasing it, because it's kind of confusing, right? It's asking kind of, can we make this new function a piecewise function where it's f of x whenever x is not equal to plus or minus 1? This is really what it's asking. Can we define a piecewise function that makes this continuous? And the answer is yes, right? All we need to do to make, these are removable discontinuities. They're called that because we can fill them in. Yeah, if we have the piecewise function equal 2 here and equal 2 here, then that fills in the holes and it's continuous everywhere. That's going to be our answer, yes. K1, hold on, let me make sure I have my K1 and K2 right. K1 is for -1, great. K1 and K2 are both equal to +2. Then G, this is what's known as a function extension. Continuous for all x. All right, I used it again. This means for all. It's like an upside down capital A. All right, and this is what's known as a function extension, which is again very common in higher mathematics. All right, so that's it. Well, nope, it's going to be a seamless transition. You're never even going to notice this happen. All right, so next one is going to be 158. 158 says, sketch a graph of this function that has the following properties. These are actually some of my favorites. I really like problems like this. It might pop up on your quiz. So we need the domain to be from 0 to 5. So like we can think of our domain as going to be 0, 1, 2, 3, 4, 5. This is our domain. So just kind of writing little notes to myself to kind of show what we need to have. The limit from the right at 1 and the limit from the left at 1 exist and are equal. So that means that the limit as x approaches 1 of this function exists, right? If the one-sided limits exist and are the same, then the two-sided limit exists. F is continuous, left continuous at x equals 2, and right continuous at x equals 3, but we only have one-sided continuity. So continuous from the left at 2, continuous from right at 3, and again, it's only continuous from the left and it's only continuous at the right at these points. Goodness, there's a lot of stuff here. And the last thing is a removable discontinuity. There's a lot here. Removable discontinuity at 1. So that's connected to this part. The limit exists. Specifically, we should make a note that it's removable. That's connected with that piece of information. A jump discontinuity at 2, that's related to this piece. And the limit, all right, so it tells us also something about 3. It's negative infinity from the left. And the limit from the right is 2. So that's all the information that we have to include. It's a lot. So let's go in order. Graph this in green. Let's go in order of all these things we have to include and try to get it. So the domain is red. The function should be defined everywhere in this red interval. And there's a removable discontinuity at x equals 1. So let's say our function is over here. There's a removable discontinuity at x equals 1. The limit from the left and from the right is the same. I don't want to go all the way to 2 yet because other things have to happen at 2. I've already made a mistake though. Why? The white part is correct. The limit exists and it's a removable discontinuity. I've got that. But we said the domain is everywhere between 0 and 5. But I have that 1 is not in the domain, so we have to put a point here. We can put that point anywhere except we can't fill in because we need a removable discontinuity. The point has to exist somewhere because a function has to be defined everywhere on this red interval. All right, let's deal with that top blue. I should have done the blue ones in different colors. There's a jump discontinuity at 2, and it's continuous from the left only. So continuous from the left means we have something like this, where the limit from the left equals the function value. It has to be a closed-in circle, continuous from the left. But it cannot be continuous from the right. And it has to be a jump discontinuity. So it's going to jump somewhere. Doesn't matter where it jumps to. Say it jumps down here. And we can move on. Let's double check that I got this right. It's a jump discontinuity. Yep. Jump discontinuity means one-sided limits exist, but they're different. And here, one-sided limits do exist, but they're different. And it's continuous here from the left, and it's not continuous from the right. That's what we wanted. It's continuous from the left because the limit exists and equals the function value. The limit exists from the right, but it does not equal the function value. So it's only continuous from the left here. Finally, it's continuous from the right at 3. From the left, it approaches negative infinity. There's an asymptote here. From the left, it approaches negative infinity. And it's continuous from the right, which means it actually does, it's only an asymptote from the left. From the right, it'll be defined somewhere. Oh, and the limit from the right is 2. So it can't be what we have. It's got to be something like this. And again, it doesn't really matter. Oh, the domain. We can't have an arrow though, because the domain is only from 0 to 5. So I'm pretty sure we've got everything. Let's do one more check through on this sort of problem. The domain of f is 0 to 5. Are we defined everywhere in 0 to 5 and only when x is going from 0 to 5? I think so. The leftmost point is x equals 0. We're defined. Yep, we're defined. We're defined. Yep, we're defined. All right, we are defined everywhere. The limit from the right of 1 and the limit from the left of 1 exist and are the same limit. The limit from the right of 1 exists, the limit from the left of 1 exists, and they are the same. Good. The function is left continuous, but not continuous at 2. It is left continuous at 2, and it's not continuous because the two-sided limit doesn't exist, so that's good. Right continuous, but not continuous at 3. Right continuous at 3, the one-sided limit equals the function value, but it's not continuous here because from the left, it goes off to infinity, negative infinity. Last, removable discontinuity at 1. Yep, we have that. Jump discontinuity at 2. Yep, we have that. And the limit as x approaches 3 from the left is negative infinity. We have that. And as x approaches 3 from the right is positive 2. So these are complicated problems. It takes a long time. Just look at how long it took me to even go through it and explain it to you. You should get some answer that looks like this. It's pretty likely you'll see something like this on the quiz. Probably not as complicated though. Do one more problem. Problem 170. Recall the discussion on spacecraft from the chapter opener. That's actually not that important. The following problems consider a rocket launched from Earth's surface. We got Earth. We got our little rocket. I don't know how to draw a rocket. Zoom. All right. The force of gravity on the rocket is given by this equation. F is a function of the distance d, and that's equal to negative mk over d squared, where F is the force of gravity. D is presumably the distance from the center of Earth. That's important. Earth should be capitalized, I think. Yep. Oh well. M, what does it say M is? Mass of the rocket. D, is it, wait, we already got that. K is a constant. Okay. What does 170 ask us to do? Determine the value and units of K, given that the mass of the rocket is 3 million kilograms. So we know M is 3 million kilograms. Find K. Well, to solve for K, just divide both sides by 3 million G. That's a math joke. Because, of course, this K is kilograms. It's not the actual constant K. Anyway, that might have been a new low for me. At least in this quarter. All right. So we just plug things in. And wait. Hold on. You just plug things in. Hold on. All right. So the force as a function of the distance is negative m, which is 3 million, times k over d. All right. I'm pretty sure this problem's getting a little cheeky. So to solve for k, right, we need to know d and we need to know the force. I think this problem is asking you to know a little bit more about physics. So it wants us to specifically say we know a point. We know a point here because when the rocket is on the Earth, what is that distance? Like we need d and we need f of d. Well, when the rocket is on the ground, this distance is the distance to the center of the Earth, 6378 kilometers. So rocket on ground. D is 6378 kilometers. It's always interesting when I do these problems without having looked at them before. Like I scan them and decide, yeah, I want to do these. Yes, I want you to do them. But doing them myself is always a little different. Now, how do we find the force of gravity of that rocket at this distance? Well, I'm not exactly sure how the book wants you to calculate this, but if you know a little bit of physics, you should know that Newton's second law says that force is equal to mass times acceleration. Fun fact, that is really only true under certain circumstances, but I'm not a physicist. I'm not going to start talking about general relativity, although I did read about it a lot this summer. I was reading some books by the guy who did The Martian. Andy Weir, I think. I don't know how to say his name though. Anyway, general relativity is really weird. We're going to use Newton's second law. The acceleration due to gravity on the surface, 9.8 meters per second squared. So F is going to be M, which is 3 million kilograms, times acceleration due to gravity, about 9.8 meters per second squared. And you can find that this F is equal to, let's use the calculator, 3 million times 9.8, going to be 29,400,000. What are the units here? Units of mass are kilograms. Right? M is kilograms. Acceleration is meters per second squared. So we have kilograms, meters per second squared. Those are newtons. 29,400,000 newtons. All right, so you have to be a little careful. This problem is actually more complicated than I originally realized. It really will flex your physics, but we really care about the force is that, but we really care about kilonewtons here because we're working in kilometers. So we have meters in this calculation. So we're really going to say that F of 6378 is 29,400 kilonewtons. All right, remember all like metric things. Kilometer is just 1,000 meters. Well, a kilonewton is just 1,000 newtons. That's the unit for force. All right, so then we can plug this in and find K this way. I will actually ask my physicist friend if there's a simpler way of doing this. This is the solution method that makes the most sense to me. The book, I looked at the book introduction. I don't think they gave you any more information to use here, but I can also look again on that, and I'll give you guys a little note above the video if I do see something like this. So we can now solve 29,400 is equal to negative 3 million times K divided by D, which again is 6378. And you can solve for K. Multiply by the denominator, divide by the negative 3 million. And you should get 29,400 times 6378 divided by negative 3 million. Or about negative 62.5044. Let me make sure that I did my steps right. 29,400 times 6378 divided by 3 million. That is our value of K here. And the units are a little bit more complicated. So the units always have to match up in an equation. So what do we have? We have force is equal to mass times K over distance. Force, we said, was kilonewtons. What were kilonewtons? Kilonewtons were kilograms, kilometers per second squared. So that's equal to mass, which is kilograms, K, which we don't know, however you want to write that, kilograms times something divided by D. And D is kilometers. All right, so again, what are we doing? We're just looking at the original function. Oh, I copied it down wrong. Negative mk over d squared. And then what happens is, what does the question mark have to be to make things even out? All right, well, we already have the kilograms accounted for. then things get a little weird. If we multiply both sides by kilometers squared, then we should get the question mark by itself. So that question mark, and again, it'll illustrate something in math that you don't have to use variables. You can use any picture you want for what you're solving for, is going to equal kilometers cubed over seconds squared. That's what the units have to be here for this to make sense. Kilometers cubed per second squared here. And if we do that, then everything should match out. I'm going to do one more check through all this because it's a pretty messy problem. Make sure I'm giving you guys the right answer and do a little review at the same time. So the force is negative mk over d squared. And I dropped the squared again. Dag nabbit. Good thing I checked my answer. Yep. Here's that squared up here. So that's squared over here, which means this is squared over here, which means that force answer is going to be a little different. Where's my eraser? All right, so it's going to be 6378 squared. Let me tab over back to my Desmos. So K is actually going to be much, much bigger. Negative 398,653. That is our constant right here. Okay. And we solve for this constant using a point that when the rocket is on the ground, we know the force being applied to it due to gravity. Force is going to be mass times acceleration due to Newton's second law. The mass is 3 million kilograms. The acceleration is meters per second squared. So we evaluated that. And again, the units of force, when you're using kilograms and meters per second squared, kilogram meters per second squared is a Newton. We converted that to kilonewtons because we are dealing with not meters, but kilometers. And we plug that in and solved for K. For the units, we again use the original formula, that force. And here we're using kilograms, kilometers, meter per second squared. That was the kilonewton on the left. And is equal to negative mk over the distance squared. M is in kilograms. K we're trying to find. Distance squared is going to be kilometers squared. And we solved for this one. Kilograms canceled. Multiplied both sides by kilometers squared and got kilometers cubed over seconds squared. That should be good to go. If it's not, I'll do a little bit more research and let you guys know. Anyway, let me know if you have any questions and have a good one.